So this week we'll look at Eulerian graphs, we'll look at the Chinese postman algorithm and how those things combine together. So the bridges of Knigsberg puzzle was something fundamental to the beginnings of graph theory, which is what D1 essentially starts from. And the question was this: was it possible to cross all 7 bridges in Knigsberg without crossing one of them twice? And Knigsberg had 7 bridges. It had 4 different islands. And, you know, it was a sort of little adventure to see if you could do it. But Leonard Euler, who was probably the smartest man in the 18th century, as far as maths goes anyway, made a bit of a breakthrough, and he realized he didn't have to think about like the real situation. He could put it into a graph. This is the same sort of thing that changes the London Underground into that familiar map. So he took the actual real world map and then simplified it and ended up with a graph that we could use here, where nodes represent the land masses of Knigsberg and arcs represent bridges that join them together. The lengths of the arcs obviously don't matter at all, it's just are they joined or not. Now the idea of starting at one point and ending at another point and crossing every single road that's possible to do is called a tour, a continuous tour specifically, hence this word here. And there's essentially one key thing here, which is that if you are on such a tour, then every trip to a node, you use 2 different arcs. So let's say if I was to start here, and I was to travel to here and then leave it, I've had to use 2 arcs, one to enter this node and one to exit this node. I then have to use an arc to enter this node and an arc to exit it, an arc to enter this node and an arc to exit it. And so if that tour exists, all of the nodes in the middle are going to be using 2 arcs at once. So that's the key thing. And then for that tour to actually exist, each of those nodes needs to have an even number of arcs coming from it. So if we're actually looking at the Knigsberg situation itself, none of these have an even number of arcs coming from it. We've got 3 here, and 5 here, and 3 here, and 3 here. So it's actually impossible to do any sort of tour that doesn't go over a bridge twice. You can sort of try it out for yourself, but imagine we were to start here, we could leave, we could get to here, we could leave, get to here. We obviously can't go back to where we came from, so maybe we keep going on to here, maybe we go to here, and then over to here, and we're sort of trapped at that point. There's no combination of arcs you can put together that will get you around that, and the way we know that is we can look at the order of the node. So order is the name for how many arcs come off a node. We've got order 3, order 5, order 3, and order 3. And we have this general thing: for a tour to exist, every node must have an even number of arcs from it, and that's if you want to end up where you started. Or if you want to start and end at different points, those can be odd. So that's what we say. It's impossible to travel over all the bridges without repeating one of them. Now, generalizing, and as this was Leonard Euler's thing, he of course names it after himself, a connected graph is Eulerian if every node has even order, and it's semi-Eulerian if 2 nodes are of odd order. So Eulerian means you can do essentially a closed tour. That means you start and you end at the same time. Whereas semi-Eulerian means that you can start at one point, you can end at another point, and cover every single arc in the interim. Any other graph that is not Eulerian or semi-Eulerian, we just say it's neither. There's not like special other names for them. And any graph that is neither, it's impossible to travel all the arcs without repeating one of them. So if we take this graph as an example, we consider the order of the nodes. So A has order 2 because there are 2 arcs coming from it, those are separate ones. B has order 4, 1, 2, 3, 4. C has order 4, D has order 2, E has order 2, F has order 3, and G has order 3. So this is a semi-Eulerian graph because 2 of the nodes are odd, that's G and F. And if we look back our definition for semi-Eulerian, it's possible to start at one of the odd nodes, travel all the arcs, and end up at the other odd node without repeating arcs. So if we start at F and if we end at G, or other way around, if we start at G and end at F, it should be possible. So yes, if we start at F, G. So let's do that. Let's actually find a route. We'll start at F, and from F we'll go to E. Let's write this down as we go through. And from E we'll go to D. Don't have very much option there. And from D we'll go to C. And then what we don't want to do is end up at G, but we've got some arcs to spare. We can come back to it later though. So C to B, B to A using one of the arcs that takes you to A to B using the other one, back to G, up to C, down to F, and finally to G. So we've got every arc was used once there, and we've got a route that starts at F and ends at G, and there's lots of different ones that would work there, so you could try a different one and it would work equally well, as long as you start and end at F and G. Now a little bit later the question gets asked, okay, well sometimes you do have to repeat arcs to make this happen. Not all graphs are Eulerian, not all networks are Eulerian, or even semi-Eulerian. So what is the optimal way of doing this? What is the closed trail, which is what we're calling this, that includes every arc which has the minimum actual weight? And what we basically have here is an algorithm where we're going to duplicate some of those paths in a way that adds the least to our total distance. It's obviously written there, but I'm going to go on to the next slide because it's written there as well, and we'll look at a real example. So here's what we've got. We've got a 5-node network, and we could imagine that these represent different villages, and the lengths represent the length of the roads in between them, and we want to visit or we want to survey all of those roads in the smallest possible time. So let's go through the process. Number one, we want to find all the nodes of odd orders. That means we need to label them up with what order they've got. So C has order 3, B has order 3, A has order 3, D has order 3, and E has order 4. Remember, order is how many arcs come from it. We want to list the combinations they could be paired and find the shortest route connecting each pair. So when I say they, I mean obviously the odd nodes. So the odd nodes were A, B, C, and D. And we have to think about all the possible ways we could combine these together. So we could combine A with B and C with D. Or we could combine A with C and B with D. Or we could combine A with D and B with C, and that should be all the combos we could do. And we want to find the shortest route that connects each pair. Now in extreme situations you do have to use Dijkstra's here, but they generally rely on you being able to spot what those distances are. So let's go through these. A to B, that's 14 is the shortest distance that I can see between the two. There's no like better route going via E, although you could count that if there was. C to D, there's a 5 that takes you there, and there's no quicker route. So A to C, so we could go A to E to C to do that. That would be 33. But it would be better to go A to D to C, wouldn't it? Because that would be a 12 plus a 5, that would be 17. So even though that's not a direct route from A to C, it goes via D, it's still the best option. That's what we want to write down here. And you might want to remind yourself what it was. That was A, D, C, because we might need to do something with that later. B to D, I think the diagonal looks like the best there. 11 plus 6 is 17. That was B, E, D. A to D, 12, yeah, we just go straight up. And B to C, 19, yeah, nothing better than that. Okay, so we've done that, listed the combinations they could be paired, and find the shortest route connecting each pair. And we want to choose the combination that minimizes this total weight. So let's add these up. So our first possible combo adds up to 19. Our second possible combo adds up to 34. And our third combo adds up to 31. And the best possible combo is this one right here at the top, A with B and C with D. And it says we need to duplicate these minimum weight paths to make the graph Eulerian. So that means that we're going to have A to B happens twice, and they've both got a weight of 14. And C to D has to happen twice, and that'll have a weight of 5. And the minimum cost is equal to the total of the original arcs plus the total of the duplicated arcs. Total of the original arcs plus the total of the duplicated arcs. Okay, so if we want to find the minimum weight of the best Eulerian graph here, and if we actually just check that point, actually, is the graph Eulerian now? Well, yeah, D now has 4 arcs coming from it. C now has 4 arcs coming from it. B now has 4 arcs coming from it. And A now has 4 as well. So that is fully traversable. We can start at any node and end at that same node and cover every road. Okay, so going to point 5, the minimum cost is equal to total of original plus total of duplicated. So the originals, just going to add these up quickly. So yeah, so the originals add up to 90. The duplicates, we've already done that. That adds up to 19 because we calculated that. And so our minimum cost is the total of those is 109. So the smallest amount of distance we would have to travel to cover all of these roads is 109 miles. And the roads that we would travel twice are those ones we just duplicated there, A to B and C to D. And you can sort of go around here and put together what this route might look like. And there's lots of different possibilities. Let's say we wanted to start at A and end up at A. We could go to B and back. We could then go to E and back to B, to C, to E, to D, to C, back to D, and then to A. That's one possible way we could do it, but there's tons of different routes you could put together there that would take you all the way around that route, and they would all have the minimum cost of 109 because we've done the least amount of roads twice that we had to. Now here's a very similar question, but we have to approach it slightly differently. It says this one, what's the weight of the shortest route which starts at B and ends at D? Now, there's a slight tweak to the algorithm here because we said that a graph that's semi-Eulerian, you can start at the odd node and end at the other odd node, and that's fine. So if we want to start at B and end at D, then they have to be odd. So let's kind of go through the same thing again, but we'll make a little tweak. So D is 3, C is 3, A is 3, B is 3, and E is 4. We've done the orders already. Now, if we want to start at B and end at D, we don't want them to become even. We want them to stay odd. So the only odd nodes that we need to list, and as far as this step 1 goes, are just A and C. And that's the only combination we need to consider. And the quickest way of getting from A to C, we've said that was the 5 plus 12 way, that was the 17. So all of our shortest route is going to be here is 90 plus 17. It's 107. That's the shortest route, which starts with B and ends with D, because it will make, so A to C duplicates this road, and it duplicates this road because we did the 12 plus the 5, and now D is even, A is even, sorry, A is even, so A's gone up to 4, D is still odd, which is what we want, C is now even, and B is still odd. So yeah, we can start at B and end at D. And then another similar question we could ask here, we want to start at D and end at E. So remember, if we want to start and end at different nodes, that means they have to be odd. So at the moment, D is odd, that's fine. But E is not. E is currently even. So we kind of need to change the sign of everything except D. So our combination of nodes that we're going to consider are A, B, C, and E here. So these are like the little tweaks you make to the algorithm when you need to. So let's go through the combinations again. And then we have to calculate what the minimum weight of those would be. So A to B, that's 14. A to C, that's 17. Done that a few times now. A to E, 18. C to E is 11. Because you can go C to D to E, so you do have to be careful there. B to E, that's just 11, isn't it? And B to C, that is 19. Doesn't look like that can be beaten. So our totals are 25, 28, and 37, so that's our best one. So we're going to duplicate A to B, and we're going to duplicate the things that take you from C to D to E. So we're going to duplicate this one, and we're going to duplicate this one. So now if we think about the orders that we've got, and bearing in mind that Eulerian, semi-Eulerian thing, we want D to be odd and E to be odd. B is now even, A is now even, D is still odd, C is now even, and E is now odd. So yeah, so we should be able to come up with a root that starts at D and ends at E. As far as like what is the weight of that root, well, we duplicated, we added 25, so it'll be 115. So yeah, there's a lot of like specifics to get your head around with this, but it's the idea that if you want to make a route fully traversable and you want to start and end at the same place, you need to make it Eulerian. You need to run this algorithm as written. If you want to start and end at different nodes, those need to be odd, so you need to think about whether you need to change them or not. So I'd say pause the video at this stage, have a go at this. This is a general getting towards an exam question version. I'm going to assume you paused and had a go. So is this graph Eulerian, semi-Eulerian, or neither? So that's just a case of working out the orders of the nodes, how many arcs come from each one, and counting them up. So we have got 4 odd nodes. And so because of that, we can just say it's neither. Because if it had 2 odd nodes, remember, we'd be able to say semi-Eulerian, and if it had 0 odd nodes, we'd be able to say Eulerian. But it's neither of those options. It is 4 odd nodes. So we want to find the shortest closed trail that starts and ends at A. So that's running the algorithm as written, where we want to make everything into even. So we'll write down our odd nodes, which are A, C, D, and F. And we'll run through all the combinations of those that we could possibly consider. And then we'll work out the distance between those. The shortest distance, so A to C, that's quite a tricky one to start with, isn't it? I guess it's 3 plus the 4, so 7. A to D is 3, A to F is 8, I think. D to F is 16, can I do better? Yeah, okay, if we go D, A, E, F, that's 3 plus 4 plus 7, that's 11. C to F, I don't really want to use that 20. 10 and 2, yeah, I think that's the best to do. So C, B, F would give me a 12. C to D is just 4, isn't it? And add them up. So our totals are 18 and 15 and 12. And the best one we've got, fortunately, is the one where everything is close together. Although I think that AF, yeah, we went AEF to do that, didn't we? So we're going to duplicate the nodes A to F and C to D. So we're going to duplicate those nodes. It says to find the shortest closed trail that starts and ends at A. So it's not actually asking for the weight of it. It means we actually have to figure out what it is. So we're going to write it down as a sort of combo. We're going to start at A. We're going to end at A. Let's go through what we could maybe do. So we could start at A and we could immediately go to B. Why not? We could go back to E, back to A, back to A again, back to E again rather, and then maybe to F from there, and back to E, maybe up to D, over to C, down to B, down to F, back to C, back to D, and back to A. So you can see this, they can be quite complicated. I mean, you've got to have a list of nodes that's about the same as the number of arcs in the thing. Okay, find the shortest closed trail that starts at F and ends at C. I went ahead and added in the actual route then. Okay, the shortest closed trail that starts at F and ends at C. So if we want to start at F and end at C, let's sort of rub out what we've got now. We want F to be odd and we want C to be odd. So all we need to combine together is A and D. Those are the only odd nodes that need to become even, and all the even nodes need to stay even. A to D, shortest route between them is just 3. So it would just be 81 plus 3 would be 84, and we could go ahead and write it down as well. Let's come up with one. So there's a possible route, but obviously there's lots that will work as long as you start at F and end at C. Here is an actual exam question, and because it's a decision exam question, it obviously has a rich interesting story behind it. Stella is visiting Tijuana on a day trip. These are the lengths of meters of the roads near the bus station. Something exams do, which those questions didn't, is they normally tell you the total lengths of all the roads. That is really useful. Make sure you don't accidentally find yourself adding them up in the exam. So she leaves the bus station at A and wants to return to A. So that's the classic Chinese postman algorithm. That's where we need to make everything even. So part A, explain why it's impossible to do that. We'd have to show that there are some odd nodes. So first off, we want to find the orders of everything. So we've got 3, 3, 3, 4, 4, 4, another 4, a 2, 3, and a 2. So why is it impossible? That would be because there are odd nodes would be enough actually. And to be extra specific, we'll say that the graph is not Eulerian. So part B says we want to find the length of the Chinese postman starting and ending at A. So that's where we have to do our pairing up of the odd nodes because we want to make everything even. The odd nodes are A and B and C and I. Maybe this is the point where you'd use Dijkstra's algorithm because C to I is going to be tricky to figure out. But we've got A and B, A and C and B and I and B and C as our combos. So we want to go ahead and find those shortest routes, which, yeah, with the I ones you've got to have a little bit of a think about them there. The actual amount they'll add up to, we've got 540, we've got a 590, and we've got a nice little 500 there. That is going to be our optimal thing, and it just wants the length. It doesn't want you to name the actual route or anything, so we can go ahead and add our 2090 and our 500 together to get our length as being 2590 meters. Part C saying is there is a statue at BC all the way up to J, but not at A, and we want to find the total number of times she'll pass a statue if she follows this route. So this is one where we're going to use the fact of that every node has to have like an entrance and exit. We're going to add up the orders of everything that we can, and we're going to do something with it. So that's with these duplicates. So A to I, which was A, D, G, I, that was duplicated, and so was B to C. And now the orders are 4 there, 6 at D, 6 at G, and 4 there. So everything's even now. Oh, and B is 4 now. Yep, okay, that'll be fine. And we want to find the number of statues she's gone past. So we're going to add up all of those orders except for the ones at A because there's no statue there, I think. Yeah, so we're going to add up everything else. So 4 plus 4 plus 6 plus 4 plus 4 plus 2 plus 6 plus 4 plus 2, and we're not adding the 4 from A. That'd be 4, 8, 14, 18, 22, 24, 30, 36. And then as each of those orders represents moving towards the place and leaving the place, if we divide it by 2, we'll get the total number of times we went to a specific, to a node. So there'll be 18 statues that she sees on her journey, or 18 times she passes a statue. Cool, one more to go. So another exam question, pause it, have a go, see what you come up with, and then we'll talk through what we should have. Okay, so we start off with the classic. We are starting at A and ending at A, so we need to find our orders of our nodes. That's a 4, that's a 3, that's a 3, that's a 4, and that's a 3. There are the classic 4 odd nodes there, so we need to pair them up in the most efficient way possible. Those are A, C, D, and F. And then let's have a little think about the shortest distance between the two. It's going to be 18 for A to C if we go A, B, C. A to D is a long way away actually, isn't it? That'd probably be the 9, 12, 11 route, wouldn't it? Yeah, going through the centre, so that's a 32. A to F, that's just a 12. And then D to F, that is a 22. C to F, I guess the 9, 12, 11 route as well. 21, 32. That's probably not the one we're going to go with, is it? C to D, is it quicker to go around? No, I think you do have to eat that 30, don't you? So we've got totals of, let's do this in green, 40, 64, and 42. So this is our best possible additional duplicate arcs. The total length of the roads was 164 miles. So 164 plus 40, 204 miles is the best we can do. We're then told a council worker starts from A, does every road once, and finishes at C. So remember, that means that they can be odd. So if A and C can be odd, then we just need to pair up D and F in the best possible way, and we've figured out earlier on that was 22. So our length of the optimal route for this council worker is 186 miles. Lastly, when a politician wants to travel every road at least once and start and end at any village, so that means we can leave any two of these odd, and what we want is the amount we're adding on for the other two odd nodes to be smallest. And if we have a look at what we worked out, this is the smallest way we can combo together any two arcs. So if we start at C and end at D, then the route should be 164 plus the 12 that takes us from A to F and duplicates that. So it'll be 176 miles would be the best we could possibly do. It says what is the optimal route though, so we actually have to work it out. So we know we're going to start at C and we know we're going to end at D. So let's sort of play this through. We may as well knock this one out of the way to start with. So I'll go CD and then back to C. Then we'll go along. So I'll go to B. And remember the AF route is the one that's duplicated. So CDCB, let's go down to E and back, so EB. Let's go to A, and then to F, to A, and back to F. It's a little bit of a faff, isn't it? Hey. And then to E, and then finish at D. So there's a possible route we could use, 176 miles. Lovely. So that's the Chinese postman algorithm.